Diagrammatic representation of electric fields. In this video we'll look at diagrammatic representation of electric fields. So Coulombs Law allows us to find the force that's acting on two charged particles. However, when we have more than two particles, 3 or 4, because the force is a vector quantity, meaning it has both magnitude and direction, we can find the resultant force acting on a particle by summing up the vectors that are applied to it. In this example, the third example here, we have 4 vectors that we are adding together, A plus B plus C plus D. Remember that we go head to tail, and the result is from the start where we started our first vector to the finish, which is our last vector. Because we're adding the vectors here, the order of addition is not important, so B plus A will be the same as A plus B. So when we are looking at 3 or more electrical charges in a space, we have to use Coulombs Law equation multiple times to determine the forces between just 2 of these to begin with, and then add up the vectors. Before we go into a little bit more detail about how to draw these diagrammatically, I'd like to first introduce 2 terms. So those are being contact forces and non-contact forces. So contact forces we might be familiar with. It's when 2 objects are touching and the bodies are in contact with each other, and that's what causes a force. So we know this maybe by a pushing force or a pulling force that we use every day. Now there are also non-contact forces where 2 bodies are separated by a distance. However, one body still applies a force to another body. This is action at a distance, and for example, we're doing electric fields topic. That's one, but then there's also magnetic fields and gravity as other examples. So how does one body know that there's another body present to experience that force? And if the distance between those 2 bodies was increased or decreased, how do the bodies know that a smaller force will be imparted on each? So in the 19th century, Faraday came up with the concept of fields to describe this interaction. When we're looking at electric fields, the most important thing for us to understand is that the field lines point in the direction that a positive test charge would travel if it was in the vicinity of that particle. So looking at the left-hand side at this positive blue particle, if we placed a positive test charge in this area here, because it's positive, being the same charge as this main charge, it will be repulsive, meaning that at that point the particle will go out that way in the direction of the arrow. Alternatively, when we have a negative charge, if we put a positive test charge in the vicinity of this particle, that arrow suggests the direction that the particle will go, like if it was released, and because they're opposite charges, it will be an attractive force, meaning it will go towards that particle. Now when there's 2 bodies in the vicinity of each other, each charge modifies the space around it, creating an electric field in that space, and they influence the field of the other particle. Okay, so what this means in terms of drawing it diagrammatically, if we have 2 opposite charges being positive and negative, and we put a positive test charge, for example, right between them, the particle, the positive particle, would want to go away from the positive and towards the negative. So that's the easiest field line to draw. However, if there was a positive test charge in this area here, it would want to go towards the negative, but away from the positive, and at that point it will be in the horizontal direction. But at every other point, if a positive test charge was placed right here, it would actually travel along this field line if it were released. If we had 2 charges that were the same, in this second diagram on the right here, and there was a positive test charge right in the middle, the forces would be balanced and the particle won't experience any motion. That's why there's no field lines in the middle, like perfectly in the middle here. And you can see if we placed a positive test charge in this vicinity, it would want to repel from both those charges, meaning it would experience an upward force in that direction. So when we're looking at multiple charges in a certain area, we think of a particle in that area being subject to the field rather than focusing on the individual particles themselves. Now, focusing a little bit more on the diagram, the strength of the field is determined by the number of lines in a certain area of space. So the more lines in a certain area of space, the stronger the field. So looking at this positive charge here, If we look really close to it, you can see there's multiple lines very close to each other. If we go further away, the lines are spaced further apart, meaning the force around that area is lower. And that makes sense because as you increase your distance from the particle, the force experienced is less. The direction of the field is tangent to the field lines, meaning it's in the exact same direction as the field lines when you draw the arrows on them. So we've seen examples of point charges. Now we're going to have a look at a plate. So in this case, we're going to look at infinitely long charge plate. And we know it's infinitely long by the diagram suggesting this plate continues with this little squiggle. As it is a conductor, the charges will distribute themselves evenly amongst the plate. So if we have an excess of electrons, it's a negative plate, and the electrons want to be as far apart from each other as possible. And when they settle down, we use the word static, so there's no charges that are moving. They will be evenly spaced apart. Any charged particle that's placed in that field will experience a force, and that force is given by the equation. Force is the electric field times the charge. Now, as the field is constant, meaning the field lines are spaced evenly apart, the force anywhere in that space will be constant. So it doesn't matter if the particle is here, here, or even further away, the force will be the same because of that spacing. Now, instead of looking at the plates being infinite, we're going to be a bit more realistic here and look at plates that are not infinite, but focus on the edge effects of the plates. Additionally, we're going to introduce a second plate and see what happens there. In this case, we've got a positive plate here and a negative plate there. Now, I know that without any symbols because of the direction of the arrows. Think about that positive test charge. We can see that both fields point in the same direction. This produces a uniform field. The word uniform is a physics term, meaning evenly distributed. But in reality, what happens is we get these edge effects where if a particle was placed here, it would be repelling from that positive plate. So it'd probably want to go out in this direction. But it would be attractive to the negative plate. So it'd be a attraction in that direction, and that's why you get the curves on the end. Lines of force always leave or arrive at right angles to the surface, and I'll go into a little bit more detail about that in another video. The lines of force never cross each other, and what that means is if they did, you've got that intersection point giving that particle a choice of two directions to go, which doesn't happen. So the field lines cannot cross each other. And when you have a uniform field, the lines are evenly spaced and the field strength is constant. Explain how the direction and strength of an electric field is represented diagrammatically.